I'd like to talk about waves. We're going to take a little bit of a detour in our study of electromagnetic theory because I can't talk about electromagnetic waves unless I at least give you a brief introduction to waves themselves. Now, you'll do a much more thorough treatment of this in Physics 211, but for now, let's just talk about some of the high points so that we can enable ourselves to learn more about electromagnetic waves, which is coming up very, very quickly. First of all, we can talk about examples of a wave. Talk about throwing a pebble into a body of water and watching the circular waves emanate from the center. We can talk about different types of waves. Mechanical waves are the kind that we're most used to seeing. There's some medium associated with a mechanical wave. So if I drop a stone in the water is my medium for those waves to travel through. And the wave is the propagation of this disturbance through the medium that carries energy but no mass. Another type of wave, which we'll talk about in much more detail later, is the electromagnetic wave. In that case, it's the only example where a medium is not required. And of course, you know the examples of the electromagnetic spectrum: light waves, and radio waves, X-rays, ultraviolet, and so on and so forth, which we will get into in a subsequent lecture. So generally speaking, when I talk about waves, we're transferring energy and we're not transferring matter. That's all we want to say by this. A mechanical wave, we need a source of a disturbance and a medium, and then some physical mechanism through which elements of the medium can influence each other and make this disturbance propagate. Simplest example, we can talk about a wave on a string. If I'm holding one end of a string and I've attached the other to a wall of some kind or some fixture, I can snap the string, and of course I'm going to create a wave down the string or a pulse down the string, if you will. And you can watch, if you wanted to, take pictures of it as it travels down the length of the rope. We see this disturbance and the bump show up at successive shots in the picture. So, in this case, the hand is the source of the disturbance, the string is the medium through which the pulse or the wave travels, and of course the individual elements of the string are being disturbed from their equilibrium position, and the elements of the string, of course, are connected together so they influence each other. The pulse has a definite height, it has a speed of propagation, and the shape of the pulse is going to change very little as it travels along the string. Waves come in two types. One type is a transverse wave. In the case of a transverse wave, we talk about a wave where the direction of propagation is perpendicular to the direction of oscillation. So in this case, if the wave is traveling this way and the oscillations are this way, this is what we call a transverse wave. Waves on a string are a really good example for this. Other examples of transverse waves: electromagnetic waves happen to be transverse waves. Waves on a string are transverse waves. Some of the seismic waves inside the Earth are transverse waves. On the other hand, if we have a wave where the direction of oscillation is along the line of propagation, that's what we call a longitudinal wave. Longitudinal wave, good example of a longitudinal wave is a sound wave. In that case, the displacement, the oscillations are in the same direction as the propagation. And then, of course, you can have a combination of the two, where we have surface water waves, for example, where we have almost nearly circular paths. That shows both a combination of a longitudinal and a transverse wave. We can talk about earthquake waves. P waves are primary waves, and those are longitudinal waves. S waves are secondary waves or shear waves. Those are transverse waves. So in earthquakes, you see both types of waves. We use a seismograph to record those disturbances and tell us about the origin of the earthquake and so on and so forth. Now we can talk about how a wave travels over time. We typically write a wave's function as a function of displacement in time in the following way. If y is the amplitude of the wave, this is a function of the x distance and velocity times time. So I have a traveling wave. If the wave is traveling to the right, I can write that as some function of x minus vt. If it's traveling to the left, I can write it as some function of x plus vt. Excuse me. The wave function, y in this case, is what we call the wave function. If you study quantum mechanics, we use the symbol psi for a wave function. In that case, we're talking about probability waves, which are a little bit different. What we like to talk about in particular are sine waves. Sinusoidal waves are ubiquitous in physics, and we'd like to see this example. We can build more complex waves out of simple sine waves by combining waves of different frequencies and amplitudes and making, in some cases, different tone qualities, for example. In this case, the wave is moving to the right. As it moves to the right, it will go from where you saw in the previous slide. You see where this red curve was to where the blue curve is, and so on as it propagates from left to right. Each element of the wave undergoes simple harmonic motion, and we can talk about building a wave model. Now, ideally, a wave is infinitely long. I can combine a bunch of ideal waves to make complex waves, and then we can also look at traveling waves. Some terminology we tend to use. The peak or crest of the wave is what we call the amplitude. It's measured in meters usually, or some unit of length. The wave length is the distance from one peak to the next, or one trough to the next. That's also measured in meters or some other length element. We use the symbol lambda for that. If I have a traveling wave, I can talk about how long it takes for one point to travel for, let's say, a series of peaks to pass a point in time. If it takes so many seconds for each point to pass, we say that's the period of the wave. Frequency is if I count how many peaks pass this point in some number of seconds, that gives me the frequency, cycles per second, or hertz. And there's a nice relationship between period and frequency. Frequency is equal to 1 over the period. As I say, for frequency, we use units of either cycles per seconds, or hertz. So in this example, we notice that we have a wave like this. The wave length is 40 centimeters. The amplitude of the wave is 15 centimeters. I can write the wave function as y equals a cosine kx minus omega t, where a is the amplitude of the wave, k is the wave number, which is equal to 2 pi over lambda. Omega is the angular frequency, which is 2 pi times the frequency of the wave, or 2 pi divided by the period. That's omega. And typically we use kx and omega t in wave equations. If I want to find the speed of the wave, I can talk about it such that the speed can be written as the frequency times the wavelength of the wave. That will tell me the speed of the wave. And so, simplest expressions to remember: frequency is 1 over the period, amplitude of the wave, a, and I can use the wave, write the wave equation as y equals a sine kx minus omega t, and the velocity as the frequency times the wavelength. We can talk about the speed of waves on a string. If I have a string that's under a tension T, I can write the velocity as the square root of the tension divided by the linear density, or mass per unit length of the string. That's a nice expression for the velocity of a wave on a string. We'll use that from time to time. And then I want to talk just a little bit about the energy of waves on a string. In this case, I can write each element of the string as having some mass dm. We can show that the kinetic energy of an element of string can be written as 1/2 mu dx times vy squared. There's a nice way to illustrate that rather than just laying it up there. Let's write it this way. If my kinetic energy of a small element of string can be written as the linear density times dx times vy squared, I know that vy is just the derivative of the wave function, so that's omega a cosine kx minus omega t. My wave function is a sine kx minus omega t. dk then can be written as 1/2 mu dx omega squared a squared cosine squared kx minus omega t, or just kx at t equals 0. So I can write my kinetic energy. So I integrate, I can write this as omega squared a squared mu over 2 integral from 0 to lambda cosine squared kx dx. If I integrate, I'll get x over 2, so it'll be mu omega squared a over 2, x over 2 plus sine 2kx over 4k, evaluated between 0 and lambda, which gives me a nice expression, mu omega squared a squared x divided by 4. So this is my kinetic energy. My potential energy would be the same. Therefore, my total energy would be just double that, or mu omega squared a squared x over 2. So that's a nice expression for the total energy of the wave. With that, I can talk about a power. A power is equal to the energy divided by the time, which would be the period of the wave. So I can write that as 1/2 mu omega squared a squared v, which is just lambda divided by the period. And so those are some nice expressions for waves. We can talk about a linear wave equation. Typically, the best way to define a wave equation is a differential equation that is second order in space and second order in time. This is a really good expression for a wave equation where y is a function of x and of t. This will apply to electromagnetic waves especially, and this is especially why I'm introducing it at this point. We will show that by manipulating Maxwell's equations in a later lecture that we can derive a wave equation for electromagnetism, and that will come in a subsequent lecture. This is a very brief introduction to waves. I want to stop here, and next time we'll talk about Maxwell's equations and how Maxwell modified Ampere's law, and then we will do a full-blown investigation of electromagnetic waves. We'll see you next time.